So how can we see a picture, a visual graph using Venn diagrams of proper subsets? Well, you would have your universe being the box, you would have A, and then you would have a circle B that is entirely inside of A, indicating that there is some element here in A that is not in B. That would be the visual representation for a proper subset. If they were subsets, potentially those two circles would be equal, and you would just title them that circle A and B. Okay? So it says determine whether the following statement is true or false. Let's give this a close look. The set AEIOU is a proper subset of the set EIOU in A. So is that a true or a false statement? Well, to me, that is a, not just to me, in general, it is a false statement. Why is a false statement? They are equal. Remember, there's two conditions. Equal being the same elements and the same number of elements. Order doesn't matter, so there's the same elements and the same number of elements. Remember, proper subset requires not only are they subsets, but they also cannot be equal. So that's a false statement. This one says, part B says, the natural numbers is a proper subset of the integers. Again, let's think about the natural numbers. The natural numbers are 1, 2, 3 on up. The integers are all negative numbers and all positive numbers. So the question is every natural number an integer? Well, that answer is yes. So that's the first thing. Every natural number is a integer. So they are subsets. That's the first thing. That's great. What's the second thing? Are they equal? Well, no, there's far more integers than there are natural numbers. So they are not equal. So if every natural number is an integer and they're not equal, then they are proper subsets. So that statement is true. Okay, let's look at 6a. Again, we're doing true and false here. It says the set 1, 4, 5 is a proper subset of the set 5, 1, 4. Hopefully you quickly knew this was false because these two sets are equal. Let's think about the next one. It says the natural numbers is a proper subset of the whole numbers. Again, natural numbers being the numbers 1, 2, 3 on up. Whole numbers being the numbers 0, 1, 2, 3 on up. So the question is, are they proper subsets? If this were a true statement, which I believe it is, we would have to write two things. First thing we have to say is every natural number is a whole number, which is absolutely true. And the second thing is we have to state they are not equal. Why are they not equal? Because 0 is a whole number and 0 is not a natural number. So they are not equal sets. So the natural numbers are a proper subset of the whole numbers. Okay, let's move on to think about it. Okay, so we can decide is something a subset or not, but could we list all the subsets? Okay, like if I said the set 1, 2, what's a subset of it? Well, the set 1, 2 is a subset of itself. We know the empty set is always going to be a subset. Are there other subsets? Well, how about the set of the number just 1? 1 would be a subset of the set 1, 2. Same thing with the number 2. 2 would be a subset of the number of the set 1, 2. So how many subsets are there? Can we figure them out? And that's what the next problems are going to get to. First, we're going to list the subsets. Second, we're going to learn how to count them. So let's look at this right now. It says some applications require that we find all the subsets of a given set. One way to find all the subsets of a given set is to use a method of making an organized list. First, list the empty set, which has no elements. Next, list all the sets that have exactly one element, followed by all the sets that contain exactly two elements, followed by all the sets that contain exactly three elements, and so on. This process is illustrated in the following example. Okay? It says set C shows the 4 condiments that a hot dog stand offers on its hot dogs. It has mustard, ketchup, onions, and relish. So I'm going to do an M for mustard, K for ketchup, O for onions, and an R for relish. Okay? So if we think about it, what are the subsets of this? Subsets of the toppings would be a possible hot dog that you could have. For instance, I could have a hot dog with ketchup. That is a subset of the toppings that are there. It is a possible hot dog that I could have. But I couldn't have a hot dog with, I don't know, how about hot sauce? Hot sauce is not one of the toppings here, so that's not a possible subset. It's not a hot dog that I could have from the cart. So the question really becomes, how many different unique hot dogs could this hot dog vendor make? Each one of those is a subset. Well, we always want to start off with the most basic set, which is the empty set. You could get a straight up hot dog with no toppings, right? Then let's consider, what if I wanted a hot dog with one topping? Well, I could have mustard, I could have ketchup, I could have onions, or I could have just relish. Those would be all the one topping hot dogs. Now we want to consider all the distinct two topping hot dogs. So I could have mustard and ketchup. I could have mustard and onions. I could have mustards and relish. So that's everything that I could have with mustard. Now let's move on to ketchup. Think about ketchup here. Would you put ketchup with mustard? Well, the answer is I'm not going to put ketchup mustard because I already put mustard ketchup. And remember, order doesn't matter. So putting a K with an M would not be in proper subset. It is not distinct from MK. So I'd have to start off with pairing ketchup with onion, and then I'd have to put ketchup with relish. Again here, repetition wouldn't make sense either. I'm going to put ketchup with ketchup. Well, that's just a hot dog with ketchup. So no repetition and order doesn't matter. This is a perfect example of roster notation. Now I've done ketchup with everything. Let's move on to onions. Again, I've already done mustards and onion, and I've already done ketchup and onion. So the only thing I can pair it left with is onions and relish. Relish has already been paired with mustard, ketchup, and onion, so no repetition there. That's it. Let's go on to three toppings. Well, I could have mustard, ketchup, and onions. I could have mustard, ketchup, and relish. Or I could have mustards, onion, and relish. That would be it for mustard. I could be paired with the other two, which would be ketchup, onions, ketchup, relish, or onions, relish. So now I need to move on from mustard, and I need to move on for ketchup. Again, I do not need to pair ketchup with mustard because I've already done all the ones with mustard. So the only thing left is ketchup, onions, and relish. So that's all three toppings. What about four toppings? Could we have a set with four toppings? And the answer is yes. In this case, we could. It could be mustard, ketchup, onions, and relish. So there's the answer to the problem. How many different hot dogs, or what are the different types of hot dogs that we can make? I've listed every single possible combination there. I do want to note something, though. I'm going to note the total possible, because we're going to view this on the next page, and I'm going to come back to it. So I'm going to go ahead and count these. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It looks like there's 16 total possible. And I want to look at how many toppings there were. There were 4 total toppings. So those two numbers I just want to write down because we're going to come back to that after the next page.